Alright, I just made a video on constructing a binary tree from an in-order and pre-order traversal, so I figured I'd do the in-order and post-order traversal since it's pretty much the same thing, just in reverse. So let me just paste this in here before I forget. Anyway, in a post-order traversal, say we're populating this array, right, with our tree. Well, all the value in a post-order traversal, all the values in the left subtree are going to go in the array first, then all the values in the right subtree will go in, and then finally we'll put the value of the root node that we started at. So this means that this last value here is actually the root node of our entire tree, right? Because we populated the entire left subtree, then the right, and then we added our root node's value into this array. Okay, so and in in-order traversal, if it was to populate this array, what it did first was it went through all the values in the left subtree, then it added the value from our root node, then it added all the values from the right subtree. So this helps us because if we know the value, if this last value is our root node, which we know it is, so this 3 is our root value, or is our root node's value, and if we find this value in the in-order traversal array, then that means that everything to the left is in the left subtree, and everything to the right is in the right subtree, right? Because of this little ordering here, L, V, R. So this would be our V, this would be our L, this would be our R. This would be our R. Okay. So given that, what we can do is so first we're going to take this value here, we're going to turn that into a node. Then we're going to find that value in our in-order array, and then we're going to recurse on the left subtree and the right subtree. And all we have to do is we just have to keep track of what our left and right bounds are for the left and right subtree. So for example, like this, the bounds of this left subtree would just be from here to here, right? 0, 0. But the bounds for the right subtree would be index 2 to index 4. And we're just going to recursively pass in the bounds to make sure we never go outside of our current subtree, if that makes sense, in the recursion. But anyway, let's actually just code this out. So let's make a map. And this is going to map all of the in-order values to their indexes, because we want to be able to find, say, the value 3. We want to be able to quickly know what index it is in our in-order array. So we're going to loop through in-order array and map the values to the indexes. Cool. Now we're going to recurse. We're going to start a recursion. So we'll call build tree. We're going to pass in, just pass in the map of in-order. This is our in-order map. I should call it in-order map, whatever. Map, we pass in the post-order array, and we're going to pass in, so post-order.length minus 1. So this is the index of the root node that we're currently processing, of the current subtree that we're processing, which in the beginning, the current subtree that we're processing is the entire tree. So what's the root node of the entire tree? It is the last thing in our post-order array. Okay. And then we have to pass in the bounds of this tree, the left and right bounds of it within our in-order array. So in the beginning, in the in-order array, the whole tree is in our bounds. So we're just going to say 0 to in-order.length minus 1. Okay, now let's start actually writing the recursion. So private tree node, build tree. We're going to pass in this map here. We're going to pass in the post-order array. And we're going to pass in, okay, what do I want to call this? This would be post-order I. We call it post-order index 2. We'll call it post-order index, be super explicit. So this post-order index represents the root of the current subtree that we are creating. So now we need the left and right bounds of our of this subtree. So we're going to call this int in order. We call it left, in order left, int in order right. Maybe I'll call it start and end. Let's go start and end. I like that better. Okay, so it's basically where is it starting in the in-order array and where is it ending in the in-order array. And this is inclusive. So like, for example, if this was 0 and this was 0, then we would return a node at index 0. So anyway, let's do the base case. So if our Postorder index is ever less than 0, because we're starting from the end and working our way down to the beginning, if it's less than 0, then we're going to return null. And we have to make sure that we actually have a subtree to process. If the size of our subtree is 0, then we don't want to do anything, right? So we're going to say if Inorder end is greater than, no wait, if Inorder start is greater than Inorder end. So if our Inorder start is ever greater than Inorder end, that means our subtree is of size 0. We don't have any nodes in the subtree, so we're just going to return null. So anyway, let's keep going. So let's actually create the node for this root, or let's create the root node for the subtree. So we'll just call it root equals new tree node. We'll pass in the value, which is just postorder index. Cool. So now we created our root node. Now we need to do root.left equals something, root.right equals something, and we're going to return the root. All right, and well, I'll do it later. Okay, so root.left. So we're gonna recurse on the left subtree, build tree, pass in the map, pass in the postorder, and okay. So for the postorder index for the left subtree, let's copy and paste. Or thinking how I want to do this. How I want to explain this. So let's just take this. All right. So in the left subtree, for the left subtree, let's look at our postorder. How does a postorder work? It would populate everything in the left subtree first, then the right, and then it would add the root node's value, right? So that meant that our root node of our whole tree was at the very end of the postorder array. Well, if this 3 is our v, what we need is the size of this R, of this right subtree. If we know the size of the right subtree, then say it was 3. If the size of the right subtree is 3, that means that this index here is the root node of our left subtree. So we need to know what the size of our right subtree is. So let's put that up here. So int right, we'll just call it right side. No, let's call it right subtree size to be super explicit. This is going to be, so actually to figure out the size of this right subtree, we need to know where this value is, this 3, in the Inorder array. Because once we know where this value is in the Inorder array, we know what the size of the right subtree is because it's everything to the right, up to the end point of our Inorder bounds that we recursively pass in. But anyway, let's first let's get this vertex, or this index here. So this is just going to be Inorder index equals, so we mapped our values earlier, which would be, I should have called this Inorder map, but anyway, this was our Inorder values to indexes, right? So we're going to pass in the value that we're looking for, and that'll give us the index that are the index in the Inorder array. So now we can do Inorder end minus our Inorder index, right? Because this, so what I'm just subtracting whatever the end of our Inorder end from our Inorder index, and that is the size of our right subtree. Okay, and now we're going to say postorder index minus 1. So what am I doing here? I'm subtracting 1 for this value here, because essentially for this root node that we just created, I'm just subtracting 1 for that. Then I'm going to subtract the size of this right subtree, which is, let's grab that right subtree size, and that will put us at the first index in the left subtree. Okay. Okay, so now we need to pass in the bounds. So in order, this will be in order start, because this is the left just say this the left bound says remains the same for the left subtree, and for the right bounds it's going to be our in order index minus 1, because we don't want to include the in order index, right? We want to, because we just processed this node, we just created a node out of this, so we do in order index minus 1. Let me fix the spacing. I'm going to rename this because this is too big. Right size. Yeah. Okay, that looks better. So this in order index minus 1, we're just subtracting 1 because we don't want to include this node that we just processed. Okay. So now we do the right subtree. Pass in the map, pass in Postorder, and this will just be Postorder index minus 1. Why? So again, so we agreed that this was the root of our tree in the very beginning. Well, if we look at a post-order traversal, it's the value, then everything in the right subtree, then everything in the left subtree. So so that means that the second to last thing in our post-order array, because we just took this, so this v is this v, this 3 is this v here, which means that the root of this right subtree must be the second to last thing in our array. All right, so that would be this 20 here. That would be the root of the right subtree. Okay, so that's why we do post order index minus 1 there. Now, where am I at now? So I passed in the index. I need to pass in the bounds. So that's going to be in order index plus 1. So this would be the new left bound for this right subtree, right? Because we don't want to include this 3, so we pass in whatever this guy is. So that would, this in order index plus 1 would be this index here, whatever. So that would be index 2 in this case, and the right bounds remain the same. So we're going to just pass in order end, and we return the root, and I think we're good. Is that everything? Let's try to run it. See if I made any typos. Cool. Submit it. All right. So that is how you do this problem. If you guys have any questions or comments, whatever, you can like, subscribe, whatever. All right. Cool. Bye.